Platypus, welcome to Platinum, where future top-notchers are made. I'm Sun-hee Celera, and today we'll explore a micromolecule that is often misunderstood but is very important, which is lipids and their role in energy storage. So come on, join me as we make our journey to top 1. So today's lesson will focus on lipids, not just as fats, but as the body's most efficient long-term energy source. You might think of carbohydrates first when it comes to energy, but what if I told you lipids are actually the real MVPs when it comes to long-lasting fuel? So, by the end of this lecture, you'll be able to first identify the basic structure and components of lipids, including common types such as triglycerides and phospholipids. Number 2, explain how lipids function as high-energy storage molecules and compare their energy yield to carbohydrates. Number 3, describe the key steps involved in lipid metabolism and how energy is released from stored fat. And lastly, 4, analyze and interpret diagrams that summarize lipid structure and storage function and metabolism. So as we start our lesson, first, let's begin with a quick scenario. Imagine you're about to go on a 12-hour hike. You only have one space for one snack. What will you bring? A slice of bread or a spoonful of peanut butter? Think carefully which one will keep you energized longer. Don't answer just yet. Keep your answers in your mind as we explore why lipids are the body's top choice for long-term energy. So, what exactly are lipids? They're organic molecules mostly made up of carbon, hydrogen, and oxygen. But unlike carbohydrates, they're non-polar and hydrophobic. Basically, they don't mix with water. So, let's go through the 3 main types. I'm sure you're all familiar with this. So, first is triglycerides. These are your body's main energy reserves made of 1 glycerol and 3 fatty acids. So number 2, phospholipids. These form cell membranes. They're amphipathic with a hydrophilic water-loving head and hydrophobic water-fearing tails. Number 3, steroids. These aren't used for energy but are important in cell signaling like hormones. So, there's a short activity that tests your observation skills. So, on your screen, there are 2 lipid molecules. One is a triglyceride and the other is a phospholipid. Can you tell which one is amphipathic, meaning it has both hydrophilic head and hydrophobic tails? If you choose the one on the left, the one with a phosphate head and 2 fatty acid tails, that's the phospholipid. You got it? The amphipathic structure of phospholipids is what makes up the double layer of our cell membrane. Now let's zoom in on fatty acids, the building blocks of most lipids. So, there are 2 main types, saturated fatty acids and unsaturated fatty acids. So saturated fatty acids, it has no double bonds, straight chains that pack tightly, solid at room temperature like butter or lard. So, unsaturated fatty acids have 1 or more double bonds. The bends or kinks prevent tight packing, liquid at room temperature like olive oil or fish oil. So quick facts. Monounsaturated fats have 1 double bond. Polyunsaturated fats have 2 or more. Most natural occurring ones are in cis form, causing the kink. And unsaturated fats are known to support heart health, lowering LDL and raising HDL. Example, compare palmitic acid, which is saturated, with oleic acid, which is a monounsaturated. Their structure affects how they behave in the body and how much energy they yield. So back to our question. Why are lipids preferred by the body for long-term energy storage? So here's the answer. Carbohydrates like glucose only has 4 kilocalories per gram, while lipids like triglycerides has 9 kilocalories per gram. That's more than double the energy. Why? Because lipids are more reduced, meaning they contain more hydrogen atoms. These hydrogen atoms hold high energy electrons, which produce lots of ATP when oxidized. So fun fact, 1 molecule of palmitate, a fatty acid, can generate up to 106 ATP, while glucose only yields about 30 to 32 ATP. Also, lipids are stored without water. Unlike glycogen, which binds water, this makes lipid compact and efficient for long-term energy storage. Most are stored as triglyceride in adipose tissue. So if you guessed peanut butter earlier, you were right. It's richer in lipids, which gives you sustained energy over a long period of time. So we learned that lipids are excellent long-term energy storage molecules. But how exactly does the body tap into that stored fat and turn it to stored energy? Let's break it down into 3 major steps. First, step 1. Lipolysis. When your body is running low on glucose, like during fasting, prolonged exercise, or even stress, it turns to its backup fuel, which is fat. This starts with lipolysis, the breakdown of triglycerides stored in fat cells or adipocytes into glycerol and 3 fatty acids, also called FFAS. What triggers this? Hormones like epinephrine and cortisol binds to receptors on fat cells. This sets off a chain reaction, which is adenylyl silyl is activated, which raises cyclic AMP, which activates protein kinases, APKA. And PKA activates 2 key enzymes, hormone-sensitive lipase (HSL), adipose triglyceride lipase (ATGL). These enzymes break down triglycerides step by step. Triglyceride diglyceride plus 1 fatty acid, diglyceride to monoglyceride plus 1 fatty acid, monoglyceride to glycerol plus 1 fatty acid. The glycerol heads to the liver to help produce glucose through gluconeogenesis. Meanwhile, the free fatty acids enter the bloodstream, but they're not alone for long. Step 2. Fatty acids are hydrophobic, so they can't travel in the blood by themselves. To get around, they bind to a carrier protein called albumin by the liver. Think of albumin like a grab driver for fatty acids. It delivers them to the tissues like muscles, heart, and liver where energy is needed. Once inside these cells, fatty acids are shuttled into the mitochondria, the cell's powerhouse, where the next process begins. Also, don't forget our glycerol body. It's water soluble, so it floats freely to the liver, whether it enters gluconeogenesis to make glucose or joins glycolysis as G3P for energy. So step 3. B oxidation. Now inside the mitochondria, B oxidation takes over. This is where the fatty acid chain is chopped down when 2 carbons at a time, producing acetyl-CoA. Each turn of this cycle also makes 1 NADH, 1 FADH2. These are sent to the electron transport chain where they generate a whole lot of ATP, our energy currency. Let's walk through what happens in energy each round of B oxidation. Activation in the cytosol, fatty acid plus CoA plus ATP becomes fatty acetyl-CoA. Then it's transported into the mitochondria using the carnitine shuttle. So the cycle steps is first oxidation produces FADH, second hydration which adds water. Third is oxidation, which produces NADH. Fourth is thiolysis, which cuts off acetyl-CoA and shortens the chain. For example, the palmitic acid, 16 carbons, goes through 7 cycles, producing 8 acetyl-CoA, 7 NADH, 7 FADH. Total ATP yield about 106 ATP from a single fatty acids. Compare that to just 30 to 32 ATP from 1 glucose molecule. Thus over 3 times more energy, making fats the real MVP for endurance. So when does this process kick in? During fasting, marathon running, low carbohydrate high diets, or stressful condition when glucose is scarce. So yes, when times get tough, your body turns to lipids as its ultimate energy backup. So let's wrap it all up. Lipids are made of fatty acids and glycerol, non-polar and energy dense. Stored as triglycerides in the adipose tissue, they provide over twice the energy of carbohydrates. When needed, they're broken down via lipolysis and B oxidation to generate ATP. This makes them preferred long-term energy source, especially during fasting or extended activity. So next time you think of fats, don't just think of weight. Think of fuel, energy, and endurance and survival. And that concludes our lecture on the roles of lipids in energy storage. And remember guys, strive, excel, and succeed. This is Platinum, where future top-notchers are made. See you on the next review.